So our next chapter in chemistry is metallurgy. Metallurgy is basically the process by which metals are extracted from their ores. So what are ores or how metals are extracted? We are going to learn about that in this chapter. So most of the reactive metals are not found in the normal form. They are not just found in the form of their actual constituent. They are either mixed up with oxygen or mixed up with any other element because they cannot exist independently. So these type of substances, which are in the form of rocks and which contain one or more metals and some other non-metals together, these type of substances are known as ores. And from this ores we are able to extract the required metal by various types of processes. And in the previous chapter in electrolysis, I told you about how electrorefining is done or how extraction of metals is done. The same thing we are going to learn in this chapter. So here we have a lot of ores given of various metals. A few names which I am telling you that you have to remember. Questions might be asked from here. So the ore of potassium is carnallite. You don't have to remember the formula, just the name. The ore of sodium is rock salt. The ore of calcium is limestone, marble and gypsum. For magnesium, again it is carnallite. As you can see, in carnallite we have magnesium, we have potassium, both. So magnesium also it is carnallite and magnesium carbonate. For aluminium it is bauxite and cryolite. We are going to learn about bauxite in this chapter. For zinc it is zinc blende and calamine. For iron it is red hematite and brown hematite. You can skip aluminium, zinc and iron for now because we are going to learn about that in detail in the next part of the chapter. And for lead it is galena. For copper it is copper pyrites. For mercury it is cinnabar. And for silver it is argentite. These are the various ores which you can remember for your own information and from the exam point of view also. Now, how are these metals extracted? Like I told you, electrolysis is the major process by which the metals are extracted from their ores, and what is used, how it is done, we will learn. But before that, let us know a few terms related to metallurgy. First of all, coming to minerals. What are minerals? The naturally occurring compounds of metals which are generally mixed with other matters such as soil, sand, limestone and rocks is known as minerals. So mineral is anything which contains the metal. Along with that, a lot of impurities are present. So minerals can be in the form of rocks, it can be in the form of crystals, it can be in the form of a powder, it can be in any form. But it does not just contain the metal, it also contains some impurities like dust, limestone, etc. Next is ore. Only these two you have to remember, the others are not essential. Ores. Those minerals from which metals are extracted commercially at comparatively low cost and with minimum effort is known as ores. So what is the basic difference between minerals and ores? Both minerals and ores are rocks which comprises of the metal and other impurities, but ores are generally applied for metallurgy. Why? Because ores can easily give the metal through a very inexpensive procedure and very quickly. As a result, ore is preferred. So ore is a type of mineral, but all minerals are not ores. Ores are the special type of minerals from where the metal can be extracted commercially in factories, in large setups, but at a very low cost and with minimum effort. You don't have to put a lot of effort, you don't have to use a lot of money for that. So those are called ores. So in our chapter we have to just study about the extraction of aluminium from its ore, and then we have to learn about certain alloys. That is it. So first of all, let us know some common ores of aluminium, iron and zinc. These are very important from exam point of view. These can be asked. So the common ores of aluminium first are bauxite, which we will learn later. Bauxite is hydrated aluminium oxide. So Al2O3.2H2O. Then we have cryolite, which is sodium aluminium fluoride. So there is sodium, aluminium and fluorine in it. So Na3AlF6. Then we have corundum, anhydrous aluminium oxide. There is no water in it, so Al2O3. These names along with the formulas and along with the chemical name is very important. Next we have ores of iron. Red hematite, anhydrous ferric oxide. There is no water in this, so anhydrous ferric oxide, Fe2O3. Then we have brown hematite. It is hydrated ferric oxide, 2Fe2O3.3H2O. Next we have magnetite, that is triferric tetroxide, Fe3O4, as the name suggests. Triferric, so 3 iron and tetroxide, so 4 oxygen. Next we have iron pyrites and siderite, but the first three are more important and generally asked in the exams. Next, talking about zinc, there is zinc blende, which is actually zinc sulfide ZnS. Then we have zincite, which is zinc oxide ZnO, and then we have calamine, which is zinc carbonate ZnCO3. So the first three from iron and the others you have to remember by heart. Let us now see how aluminium was extracted from its ore and how a metal which was so costly in the olden times became a very cheap one. Aluminium is the most abundant metal in the Earth's crust. This you have studied in the lower classes. But aluminium is very reactive in nature, so it does not occur naturally. It is mixed with various types of non-metals and other substances, and we have to extract it. Aluminium is extracted from its main ore bauxite because bauxite contains the largest amount of aluminium, and it is very easy also to extract it from this ore. Concentration of ore or purification of ore, that is conversion of bauxite into alumina, is done by Bayer's process. So how is this ore first treated? This ore is first purified and all the impurities, the dust particles and the dirt, all that is removed initially, and then the other methods are applied. So the first step, that is purification of this ore, conversion of bauxite into alumina. Alumina is nothing but Al2O3, anhydrous aluminium oxide. So that is done by a process called Bayer's process, because Bayer was the person who discovered it, so Bayer's process. So now let us see how bauxite is converted into alumina. Bauxite is grinded finely and heated to remove volatile impurities. It is then heated under pressure with concentrated caustic soda for 2 to 8 hours at 140 degrees Celsius to 150 degrees Celsius. So what is done initially, bauxite is grinded into a fine powder and then it is heated. So whatever impurities have a low boiling point, they will easily move away. They are removed. Now what is done, again bauxite is heated under pressure. A lot of pressure is applied and it is heated to 140 to 150 degrees Celsius for a very long time, 2 to 8 hours, and along with that concentrated caustic soda, that is concentrated NaOH, is also added. So this equation is known to you from the chapter analytical chemistry. So what happens when bauxite Al2O3.2H2O is treated with NaOH, concentrated NaOH at a very high temperature and pressure, it converts into NaAlO2 and it gives water. Sodium metaaluminate and water is formed. Bauxite dissolves and forms sodium metaaluminate, leaving behind insoluble impurities called red mud. So in the previous chapter we have studied about anode mud. Similarly, the impurities which are left at the bottom of the container where we were doing the experiment, this is not electrolysis, this is just a normal reaction. But even here the alumina will dissolve and the impurities will settle down at the bottom of the beaker. So that impurities is called red mud. Red mud consists of a lot of things such as ferric oxide, sand and other impurities which can be removed easily by the process of filtration. Now what happens, let's see. On diluting sodium metaaluminate with water and on cooling to 50 degrees Celsius, it gets hydrolyzed to give aluminium hydroxide as precipitate. The impurities dissolve in sodium hydroxide. So now what happens, the solution which we got in the previous step, that is diluted once again. It is a lot of water is added to it, it becomes diluted and then it is cooled. Initially the temperature was very hot, so now it is cooled to 50 degrees Celsius, and while cooling what happens, this NaAlO2 which was formed in the previous equation, that reacts with water molecules and then it forms AlOH whole thrice, aluminium hydroxide. So as aluminium hydroxide is insoluble, it will settle at the bottom, and this NaOH, all the other impurities which are still left, those impurities will remain in NaOH. It will not get deposited at the bottom. The precipitate is filtered, washed, dried and ignited at 100 degrees Celsius to get alumina. So we have AlOH whole thrice as the precipitate in the previous reaction. This precipitate is removed from the solution by filtration. It is washed over and over again, then it is dried very nicely and then it is heated at 1000 degrees Celsius, and on heating we are getting alumina, Al2O3 and water. So this entire procedure, these reactions and equations, you have to remember it very nicely. Practice it in your copy and it will easily go into your mind. The filtrate containing sodium hydroxide is again used to extract aluminium from bauxite. So this NaOH, which was formed in the second equation, NaOH, this NaOH is again used in the first process. So its NaOH is acting like a catalyst in this case. It is not getting used up, it is just circulating throughout the entire procedure. Aluminium oxide, due to its great affinity for oxygen, is a very stable compound. So this Al2O3, it is very stable. It does not decompose, it does not react with something else. It is very stable because aluminium has a strong tendency to combine with oxygen. It is not reduced easily by common reducing agents like carbon, carbon monoxide or hydrogen. Hence, electrolytic reduction was chosen as the method for reducing alumina. So, from this alumina, from Al2O3, if we want to obtain aluminium, we have to remove oxygen. And for removing oxygen, what do we have to do? We have to reduce it, because reduction means removal of oxygen. But if we use normal reducing agents like carbon monoxide and all, nothing is going to happen. Like I told you, aluminium has a great affinity for oxygen, so the bond between aluminium and oxygen is very strong. It cannot be broken easily. So the only method which can be applied is electrolytic method. We have to use electrolysis in order to remove aluminium from Al2O3 and get pure aluminium. So there is some historical data given to us here. Let's see. Difficulty faced in obtaining aluminium from alumina. Electrolytic reduction can be done in molten state only. Alumina melts at approximately 2050 degrees Celsius, very high temperature. At this temperature, aluminium vaporizes, so it was not easy to collect aluminium. So in order to do the process of electrolysis, we either use the molten condition of the compound, or we dissolve it in water. But Al2O3 is insoluble in water, so we have to melt it. But melting it completely requires a temperature of 2050 degrees Celsius, which is very high. And at this temperature, aluminium completely vaporizes. We are not left with anything. So in order to remove this difficulty, let's see what was done. This difficulty was removed by Hall, who found a suitable solvent in another ore of aluminium, cryolite. When he applied the current to the molten mixture of alumina, cryolite and calcium fluoride, he saw some shining globules of aluminium appearing at the cathode. He got elated over the success of his 3 years' concerted efforts and immediately ran excitedly to his professor and presented to him the few small pieces of the metal he had collected. So what happened? This person called Hall, since he knew that to extract aluminium from alumina, it would be a very difficult process, because if you are melting it, aluminium will vaporize. We will not be left with anything. So what did he do? He, instead of using alumina only, he used cryolite, a molten mixture of alumina, cryolite and calcium fluoride. He used 3 components together to form the electrolytic mixture. As a result, what happened, when he passed electricity through this mixture, he could observe shining globules of aluminium, that means small ball-like structures of aluminium forming at the electrode, at the cathode. Like we studied in the previous chapter, that the metal will be deposited at the cathode. So he saw that aluminium is getting deposited at the cathode. So he was very happy and he ran to his professor, because this thing had been a long point of discussion since years. And after this discovery of Hall, aluminium, which was once a very costly metal, that started being selling off at a very cheap rate. And even now aluminium is not very costly. So if Hall wasn't there, this entire process wouldn't be there till date. So we are going to learn about the electrolytic reduction of fused alumina, what would happen in the electrolytic cell, in the next video.